Okay, so only 3 questions for homework on Thursday, and the last one you had to kind of read ahead a little bit. The first 2 were concerned with the uncertainty principle, and 69, it's discussing the cyclotron in Berkeley that was built in 1930. I've actually been at the big experiment, the big accelerator that replaced the cyclotron. It's a synchrotron, and in that synchrotron we were accelerating electrons to within a very small fraction of the speed of light. But back in the day, in 1930, they were accelerating H2 plus ions to a velocity of about 4 by 10 to the 6 meters per second. So the question is, if the uncertainty in the velocity was 3%, what is the uncertainty in the position of the particles? So first thing to keep in mind is the uncertainty in the position multiplied by the mass multiplied by the uncertainty in the velocity is always greater than or equal to h on 4 pi. So we want the uncertainty in the position, so it's always going to be greater than h on 4 pi m delta v. So we have a couple of things to do. The first is to figure out the uncertainty in the velocity, and it says that the uncertainty in the velocity is 3%, or 3 parts in 100 of the velocity, which is 4 by 10 to the 6 meters per second. So the uncertainty in the velocity is 3 divided by 100 times 4 by 10 to the 6. And it is 1.2 by 10 to the 5 meters per second. So that's our uncertainty in the velocity. So we've got there. The next thing is, what is the mass of an H2 plus ion? Well, let's just say, it's going to be pretty darn close to the mass of a H2 molecule, which a mole of H2 molecules, grams, it's going to weigh that much just from the periodic table. And then we have, but we don't want that, we want molecules. So 1 mole is 6.022 by 10 to the 23 molecules. So in this way we can get grams per molecule. And this camera is really fuzzy. I've installed the driver multiple times, so I apologize for that. It's just how it is. I'm going to have to get somebody to have a look at it. Here we go. So 1 H2 molecule weighs that many grams, 3.348 by 10 to the minus 24 grams. So I'm making the assumption that an H2 molecule weighs the same as an H2 plus ion, and if I was to subtract away the mass of an electron there, it wouldn't really make any difference. Okay, so that's in grams. So the mass of an H2 plus in kilograms is going to be 1/1000th of that, because there are 1,000 kilograms. So it's going to be in 1 gram, so that's 3.348 by 10 to the minus 27 kilograms is my mass. Alright, so now we've got everything we need to substitute into that expression there. Delta x is going to be greater than 6.626 times 10 to the minus 34. I want to put the units in kilograms, meters squared, seconds to the minus 1, 4 times pi, make sure we put parentheses on everything on the bottom, times 3.348 times 10 to the minus 27 kilograms, times 1.2 by 10 to the 5 meters per second. Alright, so per seconds go, kilograms go, and 1 of my meters goes, leaving me with meters, which is a completely respectable unit for uncertainty in position, right? It's going to be a length. So here we go. See what we get. 6.626 e to the minus 34 divide, put parentheses, 4 times. Find the pi button, we don't use it that often in chemistry. 4 times pi times 3.348 e negative 27 times 1.2 by 10 to the 5. Close my parentheses, and I got 1.31 times 10 to the minus 13 meters. So we are fairly certain where that hydrogen ion is. There's not a lot of uncertainty in its principle. It's probably worth doing that calculation again on the calculator. It doesn't take long, just to make sure we got the right answer. 4 times pi times 3.348 minus 27 times 1.2 e to the 5, close the parentheses. Nope, I got the same answer the second time. I'm feeling happy about that one. Okay, so that was 69. Not too bad. They're all done kind of the same way. Alright, 70. It says, an effective treatment for some cancerous tumours involves the irradiation with fast neutrons. That's correct. The neutrons from one treatment source have an average velocity of 3.1 by 10 to the 7 meters per second. So V equals 3.1 by 10 to the 7 meters per second. If the velocities of individual neutrons are known to within 2% of the value, what is the uncertainty in the position of one of them? So delta V is 2 on 100 times 3.1 by 10 to the 7 meters per second. 2 divide 100 times 3.1. 6.2 by 10 to the 5 meters per second is my uncertainty in the velocity. Okay, now I need the mass. I'm going to have to get myself, look it up in the table in the back of the text. Mass of a neutron, close to that of a proton, 1.675 times 10 to the minus 24 grams, which is equivalent to 1.675 times 10 to the minus 27 kilograms. Whenever we're using Planck's constant, make sure your mass is in kilograms. Alright, it's looking good. So delta X m delta V is always greater than h on 4 pi. Delta X is going to be greater than h on 4 pi m delta V. Delta X is greater than or equal to 6.626 times 10 to the negative 34 kilograms meters squared per second, which are your units for h. On the bottom line, we've got 4 times pi times 1.675 times 10 to the minus 27 kilograms times, that's our mass, and then our delta V, 6.2 by 10 to the 5 meters per second. Alright, so kilograms goes, 1 of my meters goes, my seconds to the minus 1 go. Delta X is greater or equal to, let's put it in the calculator, 6.626, second function e to the minus 34, divide, very important, put the parentheses when we've got more than one thing on the bottom line there. 4 pi times 1.675, second function e to the minus 27, times 6.2, second function e to the 5, close the parentheses, and 5.08 times 10 to the minus 14 meters. Okay, alright, that's a relatively complex calculation. Let's see if we can do it again and get the same answer. Okay, having done it twice, I've got the same answer, so I'm feeling fairly confident about that. Right, looks good. Okay, so that's 7.70, 770. All right, one last question to do, which was 72, and this is the one that you had to read ahead for a little bit. Just going to move the paper up a bit. So it reads, what properties of an orbital are defined by each of the three quantum numbers, n, l, and ml. So n defines the size of the orbital, or how far on average the electron is from the nucleus. L defines the shape of the orbital. So an s orbital, L equals 0, is kind of spherical. A p orbital, which is L equals 1, is kind of a lobe, a teardrop shaped, and then a d orbital has 2 of the lobes, which is L equals 2. Okay, f orbitals have much more complicated shapes. ML, that defines the orientation of the orbital, where it is directed in space. Is it along the x-axis, the y-axis, the z-axis, or in between? Alright, so that's the homework that was assigned for Thursday.